Hi, welcome to Sunil Maths tutorial, Galois Theory, class number 13. Let us see the definition. Algebraic closure of a field capital F. Algebraic closure of a field capital F. Let us take capital F be a field and capital E is an extension of capital F. Capital F be a field and E is an extension field of capital F. Then this E is called algebraic closure. Then this E is called algebraic closure of capital F. The extension field E is called algebraic closure of the field capital F if it satisfies two properties. First one, this capital E is algebraic extension of capital F. Algebraic extension of capital F. And capital E is algebraically closed. And algebraic closure is denoted by E bar. Algebraic closure is denoted by E bar. I repeat the definition. Observe that algebraic closure of the field. Capital E is an extension of capital F. Capital E is an extension of capital F. Then E is called algebraic closure of capital F if it satisfies two conditions. The first one, E is algebraic extension of F and E is algebraically closed field. And what is algebraic extension? Algebraic extension means every element of capital E is algebraic over capital F. Every element of capital E is algebraic over capital F. Then E is called algebraic extension. What is algebraically closed? A field is called algebraically closed field if E has no proper algebraic extension. That's it. So remember the definition well and practice this definition. One of the important definition. To understand the theory part, you must learn the definitions well. So here the definition is algebraic closure. Capital E is an extension of capital F. Then E is called algebraic closure of F if it satisfies two properties. First one, E is algebraic extension of F and E is algebraically closed field, and algebraic closure is denoted by E bar. Next we are going to prove a lemma here. Please see the statement of the lemma. Let capital F be a field and sigma maps F into L be an embedding of F into an algebraically closed field L. Let E is equals to F of alpha be an algebraic extension of F. Then sigma can be extended to another embedding eta. Actually this symbol is eta. It can be written like this, eta. And E maps to L, and the number of such extensions is equal to the number of distinct roots of the minimal polynomial of alpha. I repeat the statement. Understand the statement, then it is very easy and simple to prove this. Capital F be the field and sigma maps F into L be an embedding of F into an algebraically closed field L. Define E is equals to F of alpha by an algebraic extension of F. Then the sigma can be extended to another mapping or another embedding E into L, and the number of such extensions is equal to the number of distinct roots of the minimal polynomial satisfied by alpha. Alright, we prove this theorem. Right. Let capital F be a field. Let capital F be a field and capital L be an algebraically closed field, algebraically closed field, and sigma maps F into L be an embedding of F into L, be an embedding of F into L. Then by the definition of embedding, it can be written as sigma of A is equals to A for all A belongs to capital F. Now define a mapping or define a field E is equals to F of alpha. Define E is equals to F of alpha. Be an algebraic extension of F. Be an algebraic extension of F. Be an algebraic extension of F. All these are, this is the introduction part of our lemma. Let us see. F be a field. L is algebraically closed field. Sigma maps F into L be an embedding of F into L. Embedding means 1 1 and homomorphism. By the definition of embedding, sigma of A is equals to A for all A belongs to capital F. Now define E is equals to F of alpha be an algebraic extension of F. Now we are going to prove this sigma can be extended. This sigma can be extended to another mapping. This sigma can be extended to another mapping eta that maps E into L. That is also an embedding. And the number of such extensions is equal to the number of distinct roots of the minimal polynomial satisfied by alpha. That's it. To prove this, let us define a polynomial. Let P of x is equals to a0 plus a1x plus a2x square plus and so on plus an minus 1 x power n minus 1 plus x power n be a minimal polynomial alpha, be a minimal polynomial of alpha over capital F. What is mean by minimal polynomial? It is monic and irreducible. Minimal means monic plus irreducible. Monic plus irreducible. Of alpha means P of alpha is equals to 0. Alpha is a root of this polynomial. Now consider P sigma of x is equals to sigma of a0 plus sigma of a1x plus and so on plus sigma of x power n. Since sigma is an embedding, sigma is a homomorphism, you can write like this: a0 plus a1 sigma of x plus and so on plus sigma of x power n. This condition shows us P sigma of x belongs to the ring of polynomials L of x because sigma maps from F into L. Now, if you choose x belongs to capital F and this F is subset to L, so obviously this x belongs to capital L. It means this x is algebraic over capital F. Then any element of capital F, by the definition of algebraic, then any element of capital F can be uniquely expressible as a0 plus a1x plus a to x square plus and so on plus ak x power k, where remember that this k is less than n. This k is less than n. Now define a mapping. Now define a mapping eta that maps from f of alpha into L, that maps from f of alpha into capital L as eta of a naught plus a1x plus and so on plus ak x power k is equals to sigma of a naught plus sigma of a1 into beta plus sigma of a2 into beta square plus and so on plus sigma of ak into beta power k. Beta power k. Since sigma is well defined, since sigma is well defined and embedding, sigma is well defined and embedding, so obviously you get eta, which implies as eta is also well defined and embedding of f of alpha into capital L, of f of alpha into capital L. Suppose, let us assume one point. Suppose eta of a naught plus a1x plus and so on plus ak x power k is equals to 0 implies as sigma of a naught plus sigma of a1 into beta plus and so on plus sigma of ak into beta power k is also equivalent to 0. This condition shows as sigma of ai is equals to 0 because of extension field means this set, the elements beta power k, they forms a basis for the set of f of alpha. It means every basis is linearly independent set, so the coefficients of these vectors must be equivalent to 0. Sigma of ai is equals to 0. If sigma of ai is equals to 0, then ai is equals to 0. This shows as that eta is 1 1, that eta is 1 1. Now this eta is an embedding of f of alpha into L, embedding of f of alpha into L, and an extension of sigma, which is 1 1 also, which is 1 1 mapping also. This condition shows us, this property shows us eta transforms a root of p sigma of x, a root of p sigma of x in f of alpha, into a root of p sigma of x in capital L. This point is very very important. Remember that, because eta is an embedding of f of alpha into L and an extension of sigma which is 1 1. So what it means, eta transforms a root of p sigma of x in f of alpha into another root of same polynomial p sigma of x in capital L. This shows as the number of such extensions, is equal to the number of roots of minimal polynomial of alpha. This completes the proof of our lemma. That's it. You see, now we are in the same video, we are going to prove one more theorem. Now we are going to prove one more theorem. Let us see the statement of that theorem first and then we prove it. See the statement. Let capital E be an algebraic extension of a field capital F, and let sigma maps f into L be an embedding of f into an algebraically closed field L. Then sigma can be extended to another embedding eta that maps E into L. Actually, this theorem also same as the previous lemma, but anyway we prove this. let capital E be an algebraic extension, an algebraic extension of a field capital F, of a field capital F, and sigma maps F into L, sigma maps F into L be an embedding, of capital F into an algebraically closed field, an algebraically closed field capital L. What is mean by algebraically closed field? Algebraically closed field means it has no proper algebraic extensions. No proper algebraic extensions. That's it. Now we can show that now we can show that sigma can be extended to eta that maps E into L. Right. To prove this, define a set. Define a set capital S as follows. Capital S is equals to the set of all ordered pairs K comma V such that F subset to K subset to E and V that maps K into L be an embedding. So it means capital S be the set of all ordered pairs. Capital S be the set of all ordered pairs. K comma V, set of all ordered pairs K comma V, where K is a subfield. Of capital E containing capital F, and V is an extension of sigma to an embedding of capital K into L. This is the meaning of S. Remember that. I simply define here S like this. S is equals to set of all ordered pairs K comma V where F subset to K subset to E and V maps K into L. What it means theoretically, if you explain that capital S be the set of all ordered pairs K comma V where K is a subfield of E containing capital F and V is an extension of sigma up to an embedding which maps from K into L. So trivially you observe that capital F comma sigma belongs to S. Obviously F comma sigma belongs to S because sigma is an embedding of F into L. So sigma can be extended. That's why F comma sigma belongs to capital S. The ordered pair F comma sigma belongs to S means sigma is not equals to pi. It means sigma is S. S is non-empty. So S is non-empty. Clearly S is non-empty. If S is non-empty, now choose two ordered pairs. Let K comma V dash both are in S, are taken from S. We simply write ordered pair k comma v is less than or equals to ordered pair k comma v dash if ordered pair k comma v and ordered pair k comma v dash is subset to ordered pair k comma v is less than or equals to ordered pair k comma v dash ordered pair k comma v dash because of this f is subset k. I mean the definition here, k is subset to e and k is subset to e, right? Or you remember this k dash and v dash, we define this k dash and v dash and then choose two ordered pairs. Let us take a small modification, k dash v dash are in S. Small correction, let us choose two ordered pairs kv k dash v dash are in S such that ordered pair k comma v is less than or equals to ordered pair k dash comma v dash if you conclude that this k is subset to k dash. This k is subset to k dash. This is correct. So I repeat here, we are choosing two ordered pairs kv and k dash v dash, and kv less than or equals to k dash v dash whenever we took k is subset to k dash. K is subset to k dash and theta is restricted, v dash is restricted, v dash is restricted to k is theta. V dash is restricted to k is capital V. If it is only restricted to k, then it becomes V. So right. Now obviously because ordered pair capital F comma sigma belongs to capital S, S not equals to pi, and by using this less than or equals to result, we conclude that less than or equals to is well ordering in capital S. Less than or equals to is a well ordering in capital S means the ordered pair S comma less than or equals to is a poset. Poset means partially ordered set. Every poset contains a chain. Therefore, S comma less than or equals to contains a chain. This is the property. Every partially ordered set contains a chain. So let us take this ki comma, suppose it contains a chain. So if the set of all ordered pairs ki comma vi is a chain in S, is a chain in capital S. Let us take, or we set it as k is equals to union ki over i, and define V maps k into L as follows. For an element A belongs to k implies as A belongs to ki for some i, define pi of A is equals to Vi of A. This condition shows as V is well defined. If V is well defined and we have A belongs to k, that is equals to union ki, this means A belongs to some ki for some i, maybe or A belongs to kj for some j, but either ki is subset to kj or kj is subset to ki. Ki is subset to kj or kj is subset to ki. Then by definition of chain in S, capital S, we have we have Vi of A is equals to Vi of A is equals to Vj of A. Vi of A is equals to Vj of A. Hence, we conclude that this V is well defined. This V is well defined, as well as ordered pair K comma V belongs to S. Ordered pair K comma V belongs to S, and ordered pair K comma V becomes an upper bound for the chain, the set of all ordered pairs Ki comma Vi. So the ordered pair, the chain has an upper bound. Now by using Jones lemma, we conclude that the chain has maximal element. There exists a maximal element. Ordered pair K comma eta that belongs to S. Which implies that eta maps from K into L is an extension of sigma. Now we have to prove that K is equals to E. Let us assume that K not equals to E. Suppose our aim is to show that K is equals to E. Suppose K not equals to E. We are assuming the contradictory point. We are going to prove K equal to E. So we assume that K not equals to E. So K not equals to E means there exists an element alpha belongs to capital E such that the same alpha does not belongs to capital K. Then by previous lemma, already we learned that in the same video, by using previous lemma, we conclude that the embedding eta K into L has an extension eta star that maps K of alpha into L. If that maps K of alpha into L, then ordered pair K of alpha comma eta star also belongs to S. This condition shows us ordered pair K comma eta is less than ordered pair K of alpha comma eta star. This is a contradiction. Why? Because this is a contradiction to that the maximality of K comma eta. We said that K comma eta is the maximal element of the chain by using Jones lemma here. By using Jones lemma, there must be a maximal element K comma eta for the chain. But here we get one more maximal element K of alpha comma eta star. This contradiction exists because of our assumption K not equals to E. Our assumption is wrong. Therefore, K is equals to E. Thus, we conclude that sigma can be extended to an embedding eta that maps capital E into L. This completes the proof of the theorem, hence proved. Keep learning. In the next video, we learn two more important theorems in the same algebraically closed fields. Keep learning. Wish you all the best.